Hello, my name is Jamal. This is a quick introduction to this project that was completed over the course of the spring 2025 semester at FIU, using machine learning to determine the value of an ecosystem and nature-based solution in reducing flood damage for a particular part of South Florida. So, it's part of a larger project, but I was in charge of the empirical study, and that's what we're going to focus on. We're going to focus on, the data, quick rundown, and so like the context of this is that climate change and sea level rise and urban expansion are intersecting to create this confluence of conditions which allow for more severe flooding and more frequent flooding to occur in neighborhoods in South Florida where folks are living and working, producing a livelihood. So we want to know whether ecosystem services, that is to say wetlands, mangroves, and coastal forests, have any value in mediating the excess water and reduced storm surge that is associated with their presence. So what does that mean for the research, like practically within the literature? So we found that the quantification of economic value for nature-based flood mitigation projects, one, are difficult, two, are few and far between. And I have not seen one for South Florida. If you do see one, please put it in the chat, send it to me, I'll look at it, but I haven't seen it yet. And as of April 2025, and the objective was to use two decision tree-based machine learning systems or algorithms, random forest and extreme gradient boost, XG boost, we call it XGB, and wanted to estimate the value of an ecosystem / nature-based solution to avoid flood damage. So some of the data sources that we drew on were the National Flood Insurance Program, Tamiami Canal flow data from the DB Hydro website of the South Florida Water Management District. There's a quick highlight of our methodology, so seasonal feature engineering, common filters, standard linear ones, as well as the extended nonlinear common filter. We wanted to also add the unscented common filter, which is meant to natively handle nonlinear interactions, but we didn't have enough time, so we had to cut that out. So when you look at our models, you'll see M1, M4, M5, that's because this was supposed to be a much larger project, but we cut it down to just a few models to test. We also did quantile regression and an ablation study, and the idea was to come up with some recommendations for parametric insurance products, as well as an understanding of how this could be used for flood risk land use planning. So, a very quick background. So, modeling flood risk in South Florida is not a new topic, but using flood modeling to value a nature-based solution is. What you see here is a map pulled from South Florida Water Management District's ArcGIS online repository, and this shows the extent to which the Everglades is a managed project within the Comprehensive Everglades Restoration Plan, which has been around since the 90s, since Bill Clinton was president. It is, to my knowledge, the largest joint federal and state project ever, and it is funded to the tune of several billion per year. And so the blue lines you see crisscrossing the map are rivers, canals, and streams. The more straight lines that you see further south, those are the canals that we're most worried about. Now, down here, if you can see my mouse, this is the Tamiami Canal. And Miami Dade County is pretty long, but right around here, I'd say like just under halfway is what we're looking at, because it affects a lot of the urban core that would be in the direct path of water flowing from Lake Okeechobee down to Florida Bay through the Taylor Slough. So the raising of the Tamiami Trail, which was a land bridge that cut right across the Everglades and cut off the flow, in effect containing the water, with just a few culverts allowing water to flow through, interrupted the natural flow of water and dried up a lot of the land south of the Tamiami Trail. And so the raising of the Tamiami Trail to create a bridge that's several miles long is a nature-based solution, in that it allows the natural flow of the Everglades to return to this section, particularly this section that would flow from the northern part directly north of the Redlands and then further south to Taylor Slough and into Florida Bay. So, pausing real quick, we're going to fly through this presentation to get to actually we should talk about this too. So the reining in of the Everglades is a very old project. Around 1926, if I'm not mistaken, there was a massive hurricane that wiped out thousands of people around Belle Glade, and we didn't want that to happen ever again. So a huge effort was undertaken by the United States Army Corps of Engineers to rein in the huge deposits of water that are just flowing across in a huge sheet across down the Everglades from Lake Okeechobee into Florida Bay, so that flooding wouldn't ever take us by surprise ever again. Granted, the reason why this happened was because there was a hurricane that we didn't see coming, and so we didn't ever want to. We can't control a hurricane, but we can control what's on the ground, and that is what we did. We created this crisscross pattern of canals, and one of them is the Tamiami Canal. L29 is what we call it, constructed between 1915 and 1928. And I've traveled across it. It's very long. You can literally get from Miami all the way to the West Coast, see a sunrise and a sunset in the same day. It is massive. It's very long. Now, we're not the first folks to look at the L29 canal. Anuka looked at the L29 canal and its effects on the nature-based solution of raising the Tamiami Canal, raising the Tamiami Bridge that runs parallel to the canal. They looked at how that affects particulate matter. What we're trying to understand is, how does the flow of the water relate to the building damage payout prediction of these two decision tree based machine learning models, random forest and extreme gradient boost. So, going on to the claims, we can understand that presently insurance companies are very scared to provide any sort of insurance, namely flood insurance, home insurance, disaster insurance, to anyone living in Florida, but particularly folks living in South Florida. Now, primarily that is because sea level rise, and we're just saying sea level rise because we can see the water is rising in Florida. There is no debate about that. I promise you, if you have a Bugatti and you're driving it through Miami Beach, you may no longer have a Bugatti. For the folks who are living further away from the coast, that is to say, next to the Everglades, further inland, they are also finding that their houses are getting flooded. Why would that be so? Well, because the water table underneath is getting higher. Now, for this nature-based solution, the raising of the bridge next to the Tamiami Canal, the idea is that flowing water would recharge the aquifer, which would act as a pressure gradient to repel the imposition of seawater underneath the water table, underneath our feet, into the Biscayne aquifer. Now, as it relates to insurance, the idea is that, one, it's not likely that a flash flood would happen because this area is already saturated with water. Two, fresh water would remain, and so the salt water that is coming into our aquifer would not happen as frequently. Three, we may not have to deal with sea level rise with over-engineered projects. So, while it's not directly related, it is down the line related. So I just wanted to show you this map of the claims, at least from about 7 years ago, almost 7 years ago, that there is a lot going on, and insurance companies don't like that. They don't like how much is going on. And also want to mention septic tanks. Yeah, septic tanks flow into the aquifer, and if the water table is rising, that means the aquifer is being contaminated by these septic tanks, and that is also an issue for insurance companies and also just public health generally. That's why I mentioned the intrusion of the sea water into the Biscayne aquifer. But also, just to give you some context, yeah, a lot of claims, and no one's really trying to pay all that, especially when they feel it's a losing bet. Pausing again. Let's talk about the data. So we're going to skip over the explanations of the two models. If you want to, I can revisit it, but there are folks who are smarter than me, or plenty of folks who have done the work. But I just want to get into this before this video gets too long. We're already cracking 14 minutes right now. So this is a quick overview of the data. So the NFIP data set is over 2 million rows long and 70-something columns wide. And these are some of the columns that we pulled that we felt were most relevant. So building damage amount, base flood elevation, all the way down to census block group FIPS, which is just, what districts of the census block are most affected. So geographically, like neighborhoods, clusters is what that refers to. Now for the hydrologic data, the L29 canal data, it was actually daily. So we had to create multi-day statistics, so a rolling weekly average of the measurements so that we could line that up with the NFIP claims data, because those 1,200 observations that we found are claims that are correlated, that are assigned to a particular day of the damage. But those days of damage did not line up with the days for the flow, and what's being measured here is the cubic feet per second. So we had to create some averages. In addition to that weekly average, we added a annual average, 5-year average, decadal average, and we created a managed flow indicator. So if there was anything anomalous, as well as anomalous, if there was any indication that there's a structural change in the output, it would flag it. If there was something that maybe it's not structural, but it's definitely significantly different, it would also put that in there. So maybe there was some rain that came down, and so the water that was released from Lake Okeechobee would be augmented by some precipitation. So that's what that would indicate. And for seasonality, we added sine and cosine just to cover some bases. And we funneled all of that into our data pipeline. This is a quick rundown of our method. So we had two. We started off with one class-based ablation, which you see on the right, but we had some odd-looking results, and we wondered maybe it was the structure of the code that was making things look weird. So we went with a procedural ablation. This was a lot simpler, a lot more straightforward, and because it was so simple, it ran in 30 minutes as opposed to a class-based, which took up to 3 hours for some of these. We were able to do more in terms of outputs, create more outputs for the quantiles, and wish we could have done more with the ablation. As you can see here, there's some artifacts here: M1, M4, M5. There's supposed to be 6 models plus the control, so 7 in total. But again, ran out of time and computational power. Now for the results, for the random forest class-based figures. What you see here on the right are the residual distribution and residual versus predicted. The first figure is for the control, the second is for M1, the third and final is for M4. Now for the yellow line on the quantile loss graphs, what this is referring to is how well can you trust this model. And for the control, while the residual distribution says it's pretty accurate, it's accurate enough, the quantile loss says do not trust this on any level at all. So again, control, we didn't expect it to. For M1, you can't see it, it's behind the orange line. M4, but it did well. Just feature engineering, just tinkering and making some seasonal indicators was good enough to trust the model. For the residuals, there's a bit of a spread. That spread was even, and so for different sections for different quantiles, you could get a different level of accuracy is what this is telling you. Namely, for the lower end is what this is saying, and for the M4, which is the common filter, was what I was most curious about. It filtered out all the data. So this single leaflet that you see here is characteristic of decision tree models. However, if there's just one, that means it's just putting out one prediction for all values that it could predict for, which means that it's just wrong all the time, and it should not be trusted. So 1, wrong. 2, it's wrong even though the quantile loss is near 0. So you can trust that it's wrong is what is what this model is saying. You can trust that it's wrong. Now for the XGB, the extreme gradient boost class-based figures, what we found was that super noisy, man, super duper noisy. Like the quantile loss was crazy. It's less than the random forest models, which was nice. If you flick back over here, the quantile loss was pretty low, and the predictions were not good. So there's not much that we could do here. Like, it's wrong, not trustworthy, and we wanted to know at this point, maybe it's the code, because we spent a lot of time, and we still want to know whether or not a common filter does affect anything positively or negatively. And again, the top one is the control. Oh, I forgot to mention, in the random forest model, the M5, the extended common filter, collapsed the entire model. It filtered out all of the data, so we couldn't even get a prediction or a quantile loss for that. So it failed completely, so we cut it out. But for the extreme gradient boost, the M5 was here, and similar to the M4 in the random forest model, it filtered out the data such that it was just predicting one value for all of them, all available data that it had to predict for. So going on to the procedural ablations, the random forest figures, they were decent. There was a huge variance in terms of the quantile loss, but it wasn't too bad. It was still pretty close to zero. Like the highest in terms of loss was went all the way up to 0.0016. That's not bad. It's not bad at all. When it came to the mean squared error, the prediction, it was not bad at all. Again, it's pretty close to zero. What we did find is that the common filter did make it worse. It did not help. Did not help at all. For the M4, it was okay for around the middle section, the upper middle section. So that's something to keep in mind. We'll talk about that in the discussion section. For the XGB procedural ablation, it was pretty shapely. We had a pretty good understanding of what was going on, and that is what I like to see. You know, some clean data. Now, different from the random forest of procedural ablation, we found that at the higher end, the tails, that the common filters did help in the prediction, namely for absolute error. It was pretty useful, but the common filter, the standard linear common filter, was not. The extended common filter was helpful. The standard linear common filter was not. And for the middle sections, again, lower sections, the feature engineered model was decent enough. You didn't really need to add a common filter of any kind, of any level. Now, talking about the valuation, what we found was that for the extreme gradient boost model, and talking about the data, so for a lot of the claims that were produced were claims that experienced flooding, but not all claims had a building damage amount assigned to it. So some of them had zero, but the value that was in the data set was nothing. There was nothing there. And so for our model, it did not show data, so it imputed it as nothing. There's no data. So when we found that out, what you see here is we changed the missing data to zero so that it could give us a value. And what we found is that adding that bit of knowledge, that bit of real-world knowledge to an econometric model for valuation was pretty fruitful. Up to, it's about $13 million worth for like the 90th quantile. On the lower end, the absolute lowest, about $50,000. It's not bad. Sorry, $500,000. It's not bad. It's not bad at all, especially when we're talking about the Redlands, which is mostly a farming community. These folks, they have very tight margins, so $500,000 means a lot. It really does mean a lot. It could wipe out their entire operations for the whole year. So those margins matter a great deal. So it's not nothing. Now, talking about the interpretations, what we found was that the errors rose in the random forest model, and that means you don't need to add a whole lot to the random forest for it to be useful, although it was most useful for the middle and the extreme lower tail, like the lower quantiles, right? You don't need to use a whole lot of complicated metrics or econometric models or machine learning models to get a good finding. Just because for the lower end, typically that's because if they're getting inundated, it's probably because there's a lot of water, and it doesn't take a genius to know, yeah, you've been inundated with water, even though it's a tiny bit. XGB, extended comment filters, were good for the noisy tails, and again, like for both ends, they were pretty good. And this is like for areas where like you would need to send an adjuster out there. So like areas where there's a high valuation, like the property has a high value, but there was a low damage amount predicted, you would send out an adjuster for whatever reason. I don't know why. The extreme gradient boost did pretty well for those. So that's fun. Again, I would like to complete the full ablation study with the unscented comment filter. Maybe even add in the autoencoder. Maybe that would tell me something. But playing with that might tell me something. But for the middle quantiles, a standard extreme gradient boost with a standard linear comment filter slapped onto it does pretty well. And we're not talking about huge differences in performance, but enough that if you, again, with regard to the valuation, a few percentage points related to millions of dollars for a farming community matters a lot. So it's nothing to sneeze at. Now, some of the technical limitations, if you would like to read here. Noise sensitivity. For the common filters that were placed into the XGB models, there needs to be a lot of noise. Otherwise, the common filters just filter out all the data that you would have used in the XGB. Similarly for the random forest. Now, why that's a problem for the XGB is that the XGB does a lot of tuning within it. And so, if there's no data to tune, it won't work. It's just on its back, spinning its wheels, doing nothing, a whole lot of nothing. Similarly, we're wondering that maybe the autoencoder compression might have created some bias that either introduced more errors to the model or in fact reduced the number of errors. We don't know. I would like to test this. And we only use one data set for the hydrologic data. We wanted to use both the Tamiami Canal and Lake Okeechobee water levels, as well as some other South Florida Water Management District sensors. But again, limited computation, limited time. We had to focus, lock in. Yes, so moving on. This is what we would recommend. So weaving together these models for a parametric insurance product that can predict the extremes at the tails, get a good sense of the mid-range, and also just a quick temperature check, maybe not the right terminology, but the right a regular check on the potential danger to properties in the area would be useful. And this could minimize false payouts. This could increase the speed at which those who are likely to experience some damage to their properties, increase the speed of payouts to folks who would experience damage to their properties. That would be great for them. And allow for insurance companies to have some flexibility in their insurance underwriting. Otherwise, in the upcoming flood season, which is May to October coincides with the hurricane season, we'll find that a lot of folks are out of luck in terms of coverage, insurance coverage, and they may have to move out of Florida altogether just to protect their lives and livelihoods. And so this is a solution that we think can be used now, definitely with some tuning, definitely with some more rigorous model testing. But for right now, this is a good indication of the direction that some insurance companies can go in to provide some coverage to folks in South Florida and also protect themselves from getting wiped out by a changing climate. Thank you for listening, and I'll see you in the next video.